In this session, we are going to discuss about the potential formulation in electrodynamics. We shall discuss about scalar and vector potentials, gauge transformations, and about two important gauges in electrodynamics, the Coulomb gauge and the Lorenz gauge. The three branches of electromagnetics are electrostatics, magnetostatics, and electrodynamics. In electrostatics, we deal with stationary charges so that the rate of change of Q will be equal to 0. In magnetostatics, we are dealing with steady currents where the rate of change of the current is equal to 0. Whereas in electrodynamics, we are dealing with time varying fields. The field quantities in electrodynamics are electric field intensity, then electric displacement, magnetic flux density B, and the magnetic field intensity H. Also, E and D will be coupled to B and H. The time varying fields in electrodynamics are coupled through the four Maxwell's equations. The first one is known as the Gauss's law, which is del dot E equal to 1 over epsilon 0 times rho. The second one is the Gauss's law in magnetostatics, that is del dot B equal to 0. And the third law is known as the Faraday's law, where we have del cross E equal to negative of dou B by dou T. And the final one is known as the Ampere's law with Maxwell's modification, which is del cross B equal to mu 0 J plus mu 0 epsilon 0 dou E over dou T. In the static case, if the charge density rho and current density J are given, then the field quantities E and B are given by the Coulomb's law and the Biot-Savart law. The Coulomb's law and the Biot-Savart law are mathematically expressed in these equations. Another technique to find out the fields E and B is to make use of scalar and vector potentials. In vector calculus, a vector potential is a vector field whose curl will give us the given vector field. Similarly, a scalar potential is a scalar field whose gradient will give us the given vector field. Let's see how the potential formulation becomes handy in calculating the electric field intensity and magnetic flux density, as in the case of electrostatics. From magnetostatics, we have del dot B equal to 0. Since there are no time varying fields, the curl of E will be equal to 0. If divergence of a vector function is 0, then we have already learned that that particular vector function can be expressed as a curl of a vector potential. That is, B can be expressed as del cross A, where A will be known as the vector potential. And from equation 2, since the curl of electric field intensity is equal to 0, the field can be mathematically represented as the gradient of a scalar potential. That is, E equal to negative of del V. So in electrostatics, if the scalar as well as the vector potential are available, we can easily calculate the electric field intensity and the magnetic flux density. So what about electrodynamics? In electrodynamics, we have del cross E equal to negative of dou B over dou T. The divergence equation for the magnetic field is 0. Therefore, again we can write B as equal to del cross A. But what about the solution for E? Since del cross E equal to negative of dou B over dou T, as in the case of electrostatics, we cannot express E as the negative gradient of a scalar potential. Let's try to find out whether there are any methods by which we can find out the solution for E in electrodynamics. For that, let us substitute B equal to del cross A in Faraday's law. That is, let us substitute that in equation number 3. Equation number 3 is del cross E. This is equal to negative of dou over dou T of B, which is del cross A. And this is equal to negative of del cross dou A over dou T. That is del cross E plus del cross dou A over dou T this is equal to 0. Or we can write del cross E plus dou A over dou T. This is equal to 0. Now we have a curl equation whose right hand side is 0. Curl equal to 0 implies that the function can be written as the gradient of a scalar. When we write, we have E plus dou A over dou T equal to negative of del V, and when we rearrange this equation, we'll get the electric field intensity as equal to negative of del V minus dou A over dou T. The expression for the magnetic field remains the same, which is B equal to del cross A. Let's now try to write the Maxwell's equations in terms of the potentials. When we substitute equation number 5 in Gauss's law, we have del dot E equal to 1 over epsilon 0 times rho, and this gives us del dot negative of del V minus dou A over dou T equal to 1 over epsilon 0 times rho, and that gives us del square V plus dou over dou T del dot A equal to negative of 1 over epsilon 0 times rho. So this is Maxwell's equation expressed in terms of the scalar and vector potentials. In the static case, we have the second term equal to 0. Therefore, del square V equal to 1 over epsilon 0 times rho, which is a familiar Poisson's equation. Let's find out how to write the Ampere-Maxwell's law in terms of the scalar and vector potentials. For that, let us substitute equation number 5 and 6 in the Ampere-Maxwell law. The Ampere-Maxwell law is del cross B equal to mu 0 J plus mu 0 epsilon 0 dou E over dou T. We substitute for B as del cross A, then this is equal to mu 0 J plus mu 0 epsilon 0 dou over dou T, and then in place of E we'll write negative of del V, negative of dou A over dou T. When we expand the right hand side, we have del of del dot A minus del square A. This is equal to mu 0 J plus mu 0 epsilon 0 del of dou V over dou T minus mu 0 epsilon 0 then dou square A over dou T square. Let's rearrange the terms so that the final equation reads del square A minus mu 0 epsilon 0 dou square A over dou T square. Let it be the first term, and the second term is negative of del dot A plus mu 0 epsilon 0 dou V over dou T, which is equal to negative of mu 0 J. Equations 7 and 8 are Maxwell's equations in terms of potentials. The speciality of these two equations are that they contain all information in Maxwell's equations. The differential equations for the scalar potential V and the vector potential A that is equations 7 and 8, can be written in a more symmetrical form. For that, we have to introduce a new operator, box square, as del square minus mu 0 epsilon 0 dou square over dou t square. And this particular operator will be known as a D'Alembertian. And similarly, we introduce one more operator, L, which is del dot A plus mu 0 epsilon 0 dou V over dou T. When we substitute these two operators in equation number 7 and 8, they become D'Alembertian square V plus dou L over dou T equal to negative of 1 over epsilon 0 times rho, and then D'Alembertian square A minus del L equal to negative of mu 0 J. To demonstrate equation number 9, let's start with box square V plus dou L over dou T. And when we expand this, this will be equal to del square V minus mu 0 epsilon 0 dou square V over dou T square plus dou by dou T of del dot A plus mu 0 epsilon 0 dou square V over dou T square. These two terms gets cancelled, resulting in del square V plus dou over dou T, then del dot A, and this is nothing but negative of 1 over epsilon 0 times rho, which we have proved in equation number 7. The second equation is box square, that is D'Alembertian square, A minus del L. This is equal to del square A minus mu 0 epsilon 0 dou square A over dou T square minus del of del dot A plus mu 0 epsilon 0 dou V over dou T. Now from equation number 8, this will be equal to negative of mu 0 J. So we have devised a way by which we can calculate the electric field intensity and magnetic flux density from the scalar as well as the vector potentials. Once the scalar and vector potentials are known, we can calculate E as well as B. An important observation regarding the scalar and vector potentials are that they are not unique. That means that we are free to impose some extra conditions on V and A without causing any change in E and B. That is, if we have a scalar potential V and a vector potential A, which will result in a set of E and B, we can very well have another set of V and A, which we denote as V prime and A prime, that can again yield the same E and B. We can very well find out a connection between V and V dash, a connection between A and A dash, and this is known as the gauge freedom, or the process is known as gauge transformation. That is, if we have a set of scalar and vector potentials V and A, we can very well find out another set of scalar and vector potentials V prime and A prime that will not change the functional form of E and B. Let's now discuss about the gauge transformations for V and A. That is, if we have two potentials V and A, we shall try to find out new potentials V prime and A prime, possibly a relation connecting between them, which makes the E and B invariant. That means that the sets VA as well as V prime and A prime will correspond to the same electric and magnetic fields. In terms of the scalar and vector potentials, the electric field intensity is E equal to negative of del V minus dou A over dou T. We assume that if we write del V prime minus dou A prime over dou T, this will again correspond to the same electric field. As for the magnetic flux density, we have B equal to del cross A, and if we change A to A prime, then again this will be equal to del cross A prime. We have to find out a relation connecting the primed and unprimed quantities. For that, let us take A prime as equal to A plus alpha, and then V prime as equal to V plus beta. So A prime and A differ by a quantity alpha, and V prime and V differ by a quantity beta. Therefore, E equal to negative of del V plus beta minus dou by dou T of A plus alpha, and this is equal to negative of del V, negative of dou A over dou T minus del beta minus dou alpha over dou T. But this quantity is nothing but the electric field intensity E. This implies that negative of del beta minus dou alpha over dou T equal to 0. Now for the magnetic flux density B, this is equal to del cross A plus alpha, and this is equal to del cross A plus del cross alpha. Again, this term will correspond to the magnetic flux density B, that imply del cross alpha equal to 0. Since del cross alpha is equal to 0, we can write alpha as the gradient of some scalar, that is alpha equal to del of lambda. In the next step, we will substitute equation number 13 in equation number 11. That is del beta plus dou over dou T of alpha equal to 0, and this gives us del beta plus dou over dou T of del alpha equal to 0, or del of beta plus dou lambda over dou T equal to 0. Equation number 14 indicates that the terms inside the parenthesis is independent of position, but it could depend on time. Let us call the time dependence as kT. That is beta plus dou lambda over dou T equal to kT. So let us assume that kT is the time dependence of beta plus dou lambda by dou T. From this, we'll get beta as equal to negative of dou lambda over dou T plus kT. The lambda is a time independent quantity. And we shall devise a way by which we can absorb kT into lambda. To do that, we define a new lambda equal to lambda, which is time independent plus integral 0 to t k t prime then dt prime. As a recheck, if you substitute this lambda into this equation, you will find out that beta equal to negative of dou lambda by dou t plus kt. So in the new lambda, that is lambda equal to lambda time independent plus integral 0 to t kt prime dt prime, we have absorbed the time dependent factor, that is kt. And now beta becomes negative of dou lambda over dou t. And this is the new lambda which has absorbed the time dependent factor. With the new lambda, we can write the vector potential as equal to A plus delta lambda and then V prime. This is equal to V minus dou lambda over dou t. So what does these equations tell? These equations tells us that if we have a scalar function lambda, then we can add del lambda to A and simultaneously subtract dou lambda over dou t from V to form a new potential set, that is A prime and V prime, that leaves the two fields E and B invariant. And the changes in V and A are known as the gauge transformations. We shall now show that the electric and magnetic fields are invariant under gauge transformation. We have the gauge transformation equations A prime equal to A plus delta lambda, and the second equation is V prime equal to V minus dou lambda over dou t. Here lambda is an arbitrary function of r and t. Then for the magnetic field, we have B prime equal to del cross A prime, and this is equal to del cross A plus del lambda, and this is equal to del cross A plus del cross del lambda. This term becomes 0, resulting in only del cross A, which is B, the magnetic flux density. So we have found out that when we use the new potentials A prime and V prime, that in a sense leaves the magnetic flux density unchanged. Now let us consider the case of the electric field. We have E prime as equal to negative of del V prime minus dou A prime over dou t, and this is equal to negative of del V minus dou lambda over dou t minus dou over dou t of A plus del lambda, and this is equal to negative of del V minus dou over dou t of del lambda minus dou A over dou t minus dou over dou t of del lambda. There are cancellations which result in negative of del V minus dou A over dou t, which is nothing but the electric field. So we find that we have two sets of potentials V and A, and V prime and A prime defined for E and B that will not change the functional form of E and B, provided they has to be related through these transformation relations. Let's try to solve this problem. Find the fields and the charge and current distributions corresponding to A, VRT equal to 0, and then A RT equal to negative of 1 over 4 pi epsilon 0 QT over R square along R hat direction. The second part is to use the gauge function lambda equal to negative of 1 over 4 pi epsilon 0 QT by R to transform the potentials. Let's do the first part. Here E is equal to negative of del V minus dou A over dou T, and this is equal to, since V RT equal to 0 as given in the question, this is negative of del 0, then negative of dou over dou T minus 1 by 4 pi epsilon 0, then QT over R square R hat. This is equal to 0 minus 1 by 4 pi epsilon 0 Q over R square and then R hat. So this is the electric field that we have calculated from the scalar and vector potentials that are given. Now the magnetic field is del cross A. This is equal to R hat dou over dou R cross negative of 1 over 4 pi epsilon 0 QT over R square R hat, and this is equal to dou over dou R negative of 1 over 4 pi epsilon 0 QT over R square and then R cross R. That is, the magnetic flux density is equal to 0. Now let's move on to the second part. In this case, V prime is equal to V minus dou lambda over dou T. So that means that 0 minus dou over dou T of negative 1 over 4 pi epsilon 0 QT over R, and that is equal to 1 over 4 pi epsilon 0 Q over R. Now we have the vector potential A prime, that is equal to A plus del lambda, and this is equal to negative of 1 over 4 pi epsilon 0 QT over R square along R hat plus negative of 1 over 4 pi epsilon 0 QT then dou over dou R of 1 by R R hat. This is equal to negative of 1 by 4 pi epsilon 0 QT over R square R hat plus negative of 1 over 4 pi epsilon 0 QT then negative of 1 over R square R hat, and these two terms gets cancelled, resulting in A prime as equal to 0. We shall now discuss about two important gauges in electrodynamics, the Coulomb gauge and the Lorenz gauge. We shall start with the Coulomb gauge. The Coulomb gauge is defined to be del dot A equal to 0. When we substitute this in the Gauss's law and the Ampere-Maxwell's law, which is expressed in terms of the scalar and vector potentials, that is del square V plus dou over dou T del dot A equal to negative of 1 over epsilon 0 rho. This is the Gauss's law expressed in terms of the scalar and vector potentials. Now the Ampere-Maxwell equation expressed in terms of the scalar and vector potentials reads del square A minus mu 0 epsilon 0 dou square A over dou t square minus del of del dot A plus mu 0 epsilon 0 dou V over dou t. This is equal to negative of mu 0 j. These are nothing but equations 7 and 8. When we substitute the Coulomb gauge, the first equation becomes del square V equal to negative of 1 over epsilon 0 times rho, which is the Poisson's equation. Now the second equation yields del square A minus mu 0 epsilon 0 dou square A over dou t square minus mu 0 epsilon 0 del of dou V over dou t, that is equal to negative of mu 0 j. Let's now try to understand these results, that is equation 17 and 18, a bit in detail. Equation 17 tells us that the scalar potential V satisfies Poisson's equation similarly to the electrostatic case. The only difference is that when we consider electrodynamics, the charge density rho depends on position and time, whereas in electrostatics, the charge density depends only on position. Since the charge density now depends on position and time, the solution for the scalar potential V, that is VRT, this is equal to 1 over 4 pi epsilon 0 integral rho, which is a function of r prime and t, divided by script r, then d tau prime. So this is a very interesting result. Let's try to find the meaning of this. Let's assume that somebody is moving some charges in a laboratory that is situated in Earth. So the charge density is rho, which is a function of r prime and t. When we try to record this potential in Moon, according to the equation for the potential that we wrote, that is VRT equal to 1 over 4 pi epsilon 0 times integral rho RT over script r times d tau prime. This potential will be recorded in Moon at the very instant there is a charge movement. But this will sound odd because according to the special theory of relativity, no message can travel faster than c. There seems to be a conflict, but the point is that v by itself is not a physically measurable quantity. All that we measure in Moon is the electric field intensity E, which is negative of del V minus dou A over dou T. And E will change only after sufficient time has elapsed for the news to arrive at Moon. Now the advantage of Coulomb gauge is that the scalar potential is particularly simple to calculate. And the major disadvantages are the acausal appearance of V, as we have seen in the previous example. And the vector potential A is particularly difficult to calculate, as the differential equation for A in the Coulomb gauge is a little bit complicated, as we have seen in equation number 19, which has been reproduced here. Now the second type of gauge is known as Lorenz gauge. In Lorenz gauge, we pick del dot A as equal to negative of mu 0 epsilon 0 dou V over dou T. And now this gauge is designed to eliminate the middle term in equation number 19. That is del square A minus mu 0 epsilon 0 dou square A over dou T square minus del of del dot A plus mu 0 epsilon 0 dou V over dou T equal to negative of mu 0 j. When we substitute for del dot A, this becomes del square A minus mu 0 epsilon 0 dou square A over dou t square equal to negative of mu 0 j. As for the Gauss's law, we have del square V plus dou over dou t del dot A equal to negative of 1 over epsilon 0 times rho. When we substitute for del dot A, we have del square V plus dou over dou t negative of mu 0 epsilon 0 dou V over dou t. This is equal to negative of 1 over epsilon 0 rho. This is del square V minus mu 0 epsilon 0 dou square V over dou t square equal to negative of 1 over epsilon 0 rho. Now let us try to rewrite these two equations in terms of the D-D'Alembert box square equal to del square minus mu 0 epsilon 0 dou square over dou t square. When we do that, we have the equation for the scalar potential box square V equal to negative of 1 over epsilon 0 times rho. For the magnetic vector potential box square A equal to negative of mu 0 times j. That is, the Lorenz gauge treats V and A on an equal footing. And using the D-D'Alembert, we can represent the vector and scalar potentials in a rather simple manner. Another important observation regarding these equations are that they can be regarded as the four-dimensional versions of Poisson's equation. The Poisson's equation is del square V equal to negative of rho over epsilon 0, and this is defined in 3 dimension because of the presence of the del square operator, which is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Now when we consider the D-D'Alembert, this is nothing but del square minus mu 0 epsilon 0 dou square by dou t square, and this is equal to del square minus 1 over c square dou square over dou t square, and this is equal to del square minus dou square over dou of ct square. That is, the D-D'Alembert operator can be considered as the four-dimensional Laplacian operator. Another important aspect regarding the Lorenz gauge is that V and A satisfy the inhomogeneous wave equation with a source term on the right. So we know that the homogeneous wave equation is del square f minus 1 over c square, then dou square f over dou t square, and on the right hand side we'll be having 0. Now when we use the Lorenz gauge, the corresponding equations are del square A minus 1 over c square, then dou square A over dou t square. This will be having a source term on the right hand side, that is mu 0 j. And for the vector potential del square V minus 1 over c square, then dou square V over dou t square, this is equal to negative of 1 over epsilon 0 rho. The Lorenz gauge is one of the most extensively used gauges in electrodynamics because it helps to reduce the complexity of the problems by solving the inhomogeneous wave equations for a specified source.